All right. So we've actually already talked about characteristic X-rays when we talked about sources of X-rays for XRD, right? So we already talked about K alpha 1, K alpha 2, K beta, right? And so, but we really didn't talk about the classification and how or why certain transitions happen and others don't. I think particularly there was some questions about K alpha 1, K alpha 2, why they originated from certain L shells as opposed to others. And so that's where we get into selection rules. And so that's what we're going to talk about now is what are the rules that have to happen for a given transition to occur. And so these selection rules are based on the quantum numbers. So we're going to have to do a little bit of review of that first, just to make sure that we're all on the same page there. So as we hopefully know at this point, sorry about the handwriting here, each electron is going to be defined by its 4 quantum numbers. And so those are N, L, M, and S. So you might, so these are the names that we're going to use for them. If you are used to other names for some of these, that's okay. But these are the 4 that we're going to discuss, and this is how we're going to refer to them: N, L, M, and S. So N is the principal quantum number. So and so this defines what we call the shell. So the shell is really what we're referring to here. And so the possible quantum numbers for the principal are starting at 1 and integers thereafter. So we have the first principal quantum number is 1, 2, 3, etc. So a lot of times, instead of these numbers, you'll actually see them referred to as capital letters. So K, L, M, etc. So when we talk about K, L, M, for example, back up here, the K is referring to the quantum number 1. Right? So this is the sort of the general shell when we talk about those Bohr atoms, right? How close to the nucleus is it? All right, so that's the first. So the next one that we want to talk about is the angular quantum number. And again, this is, not M, this is L. So this defines the number of subshells in a shell. So these can be integers from 0 to n minus 1. So for example, if n equals 1, then the possible numbers are 0, because then the next one would be 1, and that's equal to n. So 2 would be 0 and 1, and so forth. So that's what we're referring to in terms of the number of subshells. So how many subshells does each shell up here have? Okay, so the next one we want to talk about is the magnetic quantum number. And this one is M for magnetic. And so this defines the number of energy states in each subshell. So this has integer values again. But this time it's going to be from minus L to positive L. And that includes 0. So we can come up with all the different energy states for each of the electrons in each subshell. All right. Lastly, we have the spin quantum number, and this is S, and this defines two what we call spin moments of electrons in the same energy state. So this is saying that in each energy state we can have two electrons, each with a different spin moment. And so we refer to these different spin moments as plus or minus 1/2. Okay. So the last term that I want to bring up, because this will be part of our selection rules, is total momentum. So the total momentum for an electron is what we call total momentum, and we refer to that as capital J. And so it's actually a sum, and it's the sum of the L, or the angular quantum number, plus the spin quantum number S. So this is actually going to be part of our selection rule. So we need to know what the total momentum J is. All right, so now that we've sort of defined all of this, the big takeaway is, again, and this is something that is talked about extensively in quantum mechanics, but no two electrons in an atom can have the same set of quantum numbers. So this is a very important principle to quantum mechanics and these selection rules as well. So if you have an electron and you define its 4 quantum numbers, another electron can't have those same numbers. It can get close, but again, we have the spin quantum number to say that there's a different spin moment. All right, so I'm going to switch over here and show you various electrons defined in each shell, and we're going to look at those orbitals, and it's going to also give you the J value for those electrons as well. Okay, so this is table 6.1 in our textbook again, and this gives the quantum numbers for various electrons in the K, L, and M shells. So from all those rules, we see that the K shell, which again is n equal 1, and that means the L value is 0, we only have 1. The M value is also 0, and then there are 2 spin moments, positive and negative 1/2. So we call this the 1s orbital, and the total momentum is also 1/2. And then if we go to the L shell, we can have we have n equal 2 in this case, and then we can also have L values of 0 and 1. And then we also have multiple subshells here, and you can see all the values. So we end up having a 2s and a 2p, and their various momentums here. And you can do the same thing for the M shell. You'll notice this is the same table as in your book. I have added these lines just to sort of differentiate some of the different L values that you see. So it's a little bit more organized in my opinion. And there also are a couple errors that I've tried to fix throughout. So I've corrected it here. So if you kind of compare this to what's in your textbook, you may notice some differences. So, kind of think critically about it, and then you'll see that I've hopefully corrected the errors in this table. All right, so now that we've had a sort of review of the quantum numbers, let's get into the selection rules that we can have for electronic transitions. And so these are our three rules that we have. So a change in the first quantum number, n, principal quantum number, must be at least 1. So basically it's got to jump at least 1 shell. And so we can write this in terms of the delta of shell n is greater than or equal to 1. Secondly, the change in L, the angular quantum number, must be 1. So not greater than, but actually 1. So we can formalize this as the change in L has to be equal to plus or minus L. Or sorry, plus or minus 1. Plus or minus 1. All right, and lastly, the change in J, remember that was the total momentum, must be either 0 or 1. So we can formalize that as the delta J is equal to plus or minus 1 or 0. So those are our three rules that we have for valid electron transitions. And so these sort of explain why you don't see certain transitions. So let me switch over to the slides and let's see if we can identify particular ones that we've looked at before. Okay, so this is figure 6.2, and this is an example of some of the allowable electronic transitions. And again, we're talking about just K, L, and M shells. And this is specifically for barium. So you kind of see all the different transitions. So these are the transitions that are allowable. So if you run through these calculations, they will meet those three rules that we just talked about in terms of the change in the principal, the change in the angular, and the change in the total momentum rules that we just discussed. And so when we did that, this is an example we kind of talked about earlier. We had these alpha 1 and alpha 2 transitions. And so we see that it goes to the 1s state, the K state, and it comes from the L2 and L3. So you kind of see it starts at either L3 or L2, but we don't see one from L1. So again, this is just something that we saw before, but now we can apply that with our rules. And so we'll look at that in a second. But again, you can go through all of these, and if you're not seeing a certain transition, it's not because they wanted to make this simple, it's because it doesn't satisfy those selection rules. All right, so let's take the example of L1 to K. This is the one that we saw in the figure on the slides, is not, we don't see this. So let's look at the transitions here. So L1, we have the values of these electrons is n equal 2, L equals 0, and for K, we have n equal 1 L equal 0. So we have a transition that is greater than or equal to 1 here for n, but if we look at L, we see that the change must be 1, whereas here we're going from 0 to 0. So this already tells us this difference here, this change in L is equal to 0, so it doesn't meet rule 2. Right, so that's why we see, that's why we don't see an L1 to a K transition when we're looking at those alpha transitions. Okay, so one last thing I want to mention before we move on is what we call the Siegbahn notation. So this is the notation that we use to specify characteristic X-rays. So in fact, we've already used this when we talked about copper K alpha and so forth. So the format here is a capital English letter followed by a lowercase Greek letter, and then a subscript number. Right? So that's what we've actually seen. So again, the capital English letter, so those are K, L, M, etc. And those correspond to the principal quantum number, so Qn just for quantum number, of, sorry about that, of the electron vacancies shell. So basically where the electron is going to end up. So the end point of the electron. Secondly, the lowercase Greek letters. So this refers to the general order of the X-ray intensity. So we have alpha as the greatest intensity, followed by beta, followed by gamma, and so forth. So an example of that is the K alpha is the highest intensity of the K, again, corresponding to this, of those K intensities. So K alpha has higher intensity than K beta. So this is something we saw when we talked about filtering of these different sources. And the last thing, the subscript number that we saw also refers to relative intensity. So in this case, we have 1 being the most intense, and then followed by 2, etc. So this differentiates, for example, K alpha, where we have certain transitions, so they have the same general transition. Alpha is referring to the most intense of the K, but then even within them, there can be K alpha 1, K alpha 2, where these refer to different L subshells that you saw, right? So it's either 2 or 3. So that's sort of this whole Siegbahn notation that we've looked at before in some instances.